Welcome to a short video. My name is Andy Schweitzer, and this little video is on precipitation reactions. This is one of a couple different types of chemical reactions that we'll have in chemistry. For the most part, we have precipitation, which is a matter of solubility, acid-base, and oxidation reduction, and are really our main three types of chemical reactions. Now, what is a precipitation reaction? Well, it's a precipitation reaction and how would you recognize it? Well, it's a matter of solubility. So we're going to have two solutions. I could say a beaker here, and we have a bunch of stuff dissolved in it. Now, inside this reaction here, we're going to have some cations and some anions. They're going to be floating around separately because that's what happens to ionic compounds. They break apart when they're in solution. So the cations are floating around, the anions are floating around. I'll just put a bunch in here. This could, if it were, let's say, sodium chloride, NaCl, then this would be Na plus ions and Cl negative ions floating around inside here. And then they're quite soluble there. Okay, then we're going to have another beaker, which is going to, let's just say, have more cations dissolved in it and more anions. And let's say this one is silver nitrate, which would be AgNO3, and this thing, of course, they're separate here, would be Ag plus ions and NO3 negative 1 ions. So there's two things with ions dissolved. So first of all, how do we recognize a precipitation reaction? We're going to have two ionic compounds, two solutions mixing together to form one new compound, one new solution. So one, they're going to be liquid. We could write like this. I'm now going to mix this guy with this guy, and I would write it out simply like this: NaCl plus AgNO3, and this would be my reactants that I'm mixing together in this solution. In a nutshell, what happens is and this is kind of a theme that I really try to focus on, is that even though these two ions here are soluble in their own environments, when you put them together, you end up having some of them stay soluble, and at this point we won't mention which ones, but some of the ions and cations mixed together form an insoluble salt, which will fall to the bottom. Now, salt, I'm meaning it's going to be an ionic compound. In this case, the ions in this one will be the sodium ions. They will still be floating around. The nitrate ions will be floating around, but on the bottom will be the silver chloride. That will fall out. So in this case, it will be NaNO3 will remain aqueous, and we know aqueous means dissolved in water, but the AgCl will be solid. Okay, that falls at the bottom. So this is your typical chemical reaction. Again, I would focus on how do you recognize one? Well, you have two aqueous solutions, two ionic compounds, so a cation, anion, and we're just a matter of putting them together, and different combinations of different ions have different solubilities, and that's a pretty big focus point. Different combinations of different, I guess go with that, good enough. Different combinations of different ions have different solubilities. meaning that just because they're dissolved here, when we mix them together, in fact, we combine the silver ion with the chloride ion. All of a sudden, we got a situation where the solution was holding too much and couldn't hold it. Is there still some silver ions floating around up here? Yes, although it's very small. Chloride ions, yes, but very small. So either way, it's purely a matter of solubility in the sense that the combination of the silver ions and the chloride ions together maxed out their particular solubility. Therefore, it fell out. It got saturated. The sodium nitrate has yet to meet its solubility yet. It still can dissolve more, so it's a very soluble substance, so it dissolves very easily. All right. So, how do you predict the products of an ionic, of a solubility precipitation reaction? I'm going to go back to my same equation. I have AgNO3, and I have NaCl. Now, this is a simplistic way of looking at it, but we have our +1 cation, -1 anion, +1 cation, -1 anion. Now, these are both soluble, AQ. We'll assume that they are dissolved in water. So my potential products would be different combinations of different ions that have different solubilities. So my only option here to find out a different combination that might be less soluble would be one cation with the other anion. Two cations will not go together. You need cation and anion. So this is one option that might form a substance that has a very low solubility, so it doesn't hold much in the solution, so it falls out. NaNO3 +1 -1. Make sure you crisscross or charge balance on the product side. Then you have the silver, and the chloride is your other option. AgCl +1 -1. Make sure you charge balance. I've just predicted my potential products. Now, I still need to determine whether they're aqueous. I'll just put a question mark here. Or whether they're solid. Now, keep in mind, if it is a solid forming, meaning it precipitates, we would use an S. That means it is insoluble. If it is an AQ, this means it will be dissolved, and we would say aqueous. All right, and the term for that would be soluble. So some kids get just mixed up because S, does that mean soluble? No, it means insoluble or solid. We could also have an L, would be for a liquid, not dissolved, just purely liquid. And the only time we'll really see that a whole lot in these types of reactions is where we have HOH formed, which is liquid water. Of course, you could write it like that, or we could write it like H2O liquid. Okay, I will do, let's just say, one more example where we're just going to predict some products. Let's take another example here. I'll talk about this concept on the next slide here, but let's try another example. Let's go with sodium carbonate. Notice I'm writing my ionic compounds charge balanced, and let's go with barium nitrate, and that would require a 2 charge here. All right, so cation +1, and this is +2, and then -1. Now, I like to write the charges above them. On the AP exam, they don't like that a whole lot, but the charges will never change in this type of reaction. So when I rearrange them, again, this cation goes with this anion. So cation is always written first, carbonate, plus 2 -2, and then we have sodium nitrate, NaNO3, +1 -1. I'm not done yet. I would require myself to have at least one solid form. Like I said, I haven't discussed yet how we determine whether it's a solid yet. But I have now predicted my potential products, at least on paper. Okay. Now, how do you end up predicting these particular products, states? That is on my next slide here. Now, I'm going to do this first example, which is going to be the silver nitrate and sodium chloride. So I have my reaction. I already predicted my products. AgNO3 plus NaCl yields AgCl, and I mentioned in the very first slide that that one forms a solid, and then I have NaNO3. I have to predict my products on both of them. Now, I will note for just initially on that in order, let's see what we have here. At least one precipitate. Okay, and we'll move this right here. Now, you can have two. Okay, that's fine too. But you have to have at least one thing forming a solid. Otherwise, there's nothing has to change. It's the same as it was before. I'll explain more about that later. But you also, another acceptable reaction would be is water forming. We'll also take that as a new substance being formed, and it's actually a type of reaction called a neutralization reaction. A little different, but it looks very similar. So now, how do I know if I get one of these? Now, if they're both end up being aqueous, then this would be a no reaction, and we just simply create no reaction. Nothing has changed, and I'll explain more about a no reaction in a minute. But how do I know if these are aqueous or solid? The only liquid we would be water, and there's not water here. They're dissolved in water, but they're not making water. Okay, so first thing I do is this. On the old style AP exam, you would say that they would have no reactions. So there always would be something formed, but on a lot of stuff we're doing in class, a no reaction is a definite possibility. So the first thing I do is look at what's called a quick check. And these are very common options that are very soluble. You know, the ones that are always aqueous or soluble. That'd be AQ. Okay, and you will see this on our particular worksheets all the time. And they are sodium ions, and I will put a little X here because it's part of an ionic compound, and it doesn't matter what the anion is. If you have sodium as a cation, this thing is going to be always aqueous. Potassium ions and the anion. Doesn't matter. This thing will be aqueous. And ammonium NH4+. All right. Again, always aqueous. Very soluble compounds. And the last one actually is an anion, and that is nitrate. NO3-1. Anytime you have a salt that contains one of these guys, it is aqueous. Okay. So right off the bat here, I could go up to my problem set and say, okay, well, this guy contains a sodium and a nitrate, so either one would be fine, but this one is AQ. All right. Now, we don't have any of those two here, so we need to turn to our solubility chart. All right, so the solubility chart works like this, and I will simply click over to my solubility chart, which you can get on my website. You should have it in your workbook. If you don't, you can get it off my website. It would be, if you go to my website, which I don't know that I have up here right now. I do. Okay, so this is my current website at this very moment. Could change. Who knows? Science resources, solubility chart right there. All right, so at this point, I will just pull this up right here. That's the solubility chart. And as you look at this solubility chart, you'll notice that it says here, the top section here, it says, okay, and I can't write on here anymore because I'm no longer in the correct program, but this right here is soluble. This is AQ, okay, always soluble. These guys, if they're present, are always soluble, and there are no exceptions to this guy. But here, if the fluoride is our anion, then it's always going to be soluble unless this is one of the cations. So magnesium fluoride is insoluble, calcium fluoride, strontium fluoride, barium fluoride, and lead fluoride. Okay, so these ones are always soluble. These are the exceptions. Just in the bottom, it says, okay, these are the ones that are always insoluble, and these are the exceptions. Now, everything, and here's my quick checks. Anything here is, things are always somewhat soluble. I mean, lead fluoride has some solubility. It could be literally on the factor of 10 to the negative 10th, meaning that 1 every 10 billion molecules dissolves. This is generally considered soluble, generally considered insoluble. There are some exceptions. Okay, so we're looking at silver chloride. So what I do is I look to my anion. This chart mostly works off the anions. It's got some exceptions here. So go find a chloride. And here's chlorides, bromides, and iodides. So chlorides are generally soluble. And I would want to put AQ there unless I have one of my exceptions, and that is silver. The exception, therefore, this thing is insoluble. I'll flip back to my chart here, and again, because this is one of my exceptions, I will put a solid here, and I would go ahead and balance it, and this one looks like it's already balanced. All right, let's do the other one. Okay, I gave the barium nitrate problem last time. I'll do this one. Okay, we'll just do it right here. I got barium carbonate, so I want to find carbonates. Let's go find, well, let's do the quick check first. I have here, again, sodium nitrate. Either one would work. This thing is AQ. And the barium carbonate, looking for carbonates. Now, carbonates generally are insoluble. In fact, they're only soluble if it has a sodium, potassium, or ammonium hook to it. So this one will not be insoluble. Or will not be soluble, it'll be insoluble. There we go. And I'll therefore put an S right here and balance it, and I'll be done. And this one, 2 nitrates, I put a 2 here, 2 sodiums, and I have 2 sodiums. That one's now balanced. All right, so let's go on to our last slide. And of course, these particular reactions take a little practice, and you'll have to try some of them and have some success, have some failures, but try them until you figure them out real well. All right, so I'm going to again talk about 3 things: molecular, ionic, or net ion equations. All right, so this equation, I'll stick with the one I started with, AgNO3 plus, let's say, what was it, NaCl yields AgCl plus NaNO3. This is called a molecular equation because we're holding everything together as molecules, even though we know from previous chapters that ionic compounds don't stay together. So even we're writing them on paper, AQ and AQ, that we're writing on paper together, but in reality, in the jar, they're separate. They break, cation, anion, cation, anion, and they separate. The only one that's not separate here, even though we have a cation anion here, is this guy formed a solid. On my previous first slide, you will find that I wrote all of these separated, but there's my silver chloride. All right, so this is called your very typical way to write this type of reaction is like this, even though there's some fallacies here. These are not actually together. So molecular equation, okay, very common way to do it. Next up is what's called an ionic equation. Not as common, but anything that's actually an ion, you write as an ion. So I would split these. Can't split that one because it's together as a solid on the bottom of the jar. And I would split these. So I have Ag plus NO3 minus 1 plus Na plus 1 plus Cl minus. That's what the initial stuff looks like, two separate beakers. And then we mix them together, and I get this AgCl, forms a solid, and I get Na plus 1 plus NO3 minus 1. These are still not together. I could get them to go together if I evaporated out all the water and therefore crank the concentration up higher, get these things to literally have to get into a smaller and smaller area, and finally the concentration reaches high enough where they would precipitate, and even eventually take all the water out, they just form a solid. But either way, this is called an ionic equation. A net ionic equation is one where we eliminate. The net ionic equation removes what we call spectator ions. This is an ion that just simply does not change from start to finish at all, in any way whatsoever. Charge, number, quantity, bonding, it's same before, same after. The silver, for example, is not a spectator ion. It goes into forming this compound. The chloride also goes into the compound, but the nitrate and the sodium are, they're essentially the same thing. So I would remove spectator ions like these guys, and just simply write out the reaction without them. They're there before, they're after, they're really not doing anything. This guy would be Ag plus Cl minus yields AgCl. This is it. You could write this as a solid if you'd like. Actually, pretty common way of writing out these chemical reactions. Okay. This method of molecular, ionic, net ionic is a great way to show a null reaction. Let's say, for example, we are doing, let's go ammonium NH4 nitrate. Okay, this is an example of a no reaction. Okay, and I'm going to mix this with sodium chloride. Right, this is going to produce. Okay, I can predict my products. I got cation, anion, cation, anion. I'll put my different combinations of different ions, have different solubilities. So I'll just predict what I could possibly have. This cation, that anion, NaNO3. And I have ammonium chloride, NH4Cl. Okay, so in this case, just because I wrote them on paper doesn't mean they're going to fall out of the beaker. These are potential products. Make sure you balance the charges on all ionic compounds, and we're all done here. Do a quick check. All right, so this guy contains sodium and nitrate, so this guy is AQ. This guy contains ammonium, so this guy is going to be very soluble, AQ. At this point, there's nothing that's going to actually happen. We would write down no reaction, okay? And that would be done. But let's try and show this as a ionic or net ionic equation. This is called molecular. If without knowing anything about this, you might think something actually happened. I put it on paper, this thing's rearranged, but in reality, nothing happened. So the ionic equation and the net ionic equation will show my point here. The ionic equation would put anything that's actually ionic, aqueous, which is all four of these guys, two liquids being mixed together. Nothing fell out. So what's it look like? Split up the ions. NH4 plus NO3 minus plus Na plus Cl minus yields Na plus NO3 minus plus NH4 plus Cl minus. This is the dynamic equation. And the order which I list them on the equation has no meaning. So really, this side is no different than this side. And in fact, if I were to try and write a net ionic equation, you would simply be eliminating everything. Everything would be getting eliminated because nothing changed, and there would be no net reaction, no net ionic equation, so it still would be no reaction. That's pretty much it for precipitation reactions. This should be followed up with plenty of work on your practice problems, and make sure you ask if you have any questions.